Okay. And then to celebrate, this is a languages conference where we all handle multiple languages. In honor of our program chair, I will do this talk in Danish. Actually, better not. So when I was invited to give this talk, I was sort of nervous and I had some ideas, and in the end I agreed to give a talk on this. And a couple of months later I realized I'd gotten myself into big trouble, because what I would really do is really hard to do in an hour, and really takes a lot of sort of getting the background in place before you can generalize from it. So it would be easy to give a talk that's full of motherhood and apple pie and not say anything. I will try not to do that. This is sort of my list of things I'm trying to do. You will find that it's somewhat incomplete in what I actually do after this. I can't do it all, but I'm around. You can talk to me. There's the panels and such, and there's the questions. And please do remember the bottom thing here. I don't believe in perfect languages, and I don't believe I have all the answers in language design. So I'm going to try and set a little bit of the context. What are we talking about? Where did C++ come from? What are the problems that we've been trying to solve with it? I will mention a few language myths, which I think do a fair bit of harm to a lot of languages and to the discussion about languages. Then I will point out that a lot of what we are doing is not actually language technical, going to what's going on in the community and the discussion about languages, and then I will actually get to a little bit of code in the end to illustrate a few points. And when I started on C++, the world was very different from today. People sometimes forget that. And I mean, Ken and Dennis had just managed to demonstrate that you could take an operating system, write it in a higher level language, C, and then port it to another machine that's not the same architecture. This was well known to be impossible. Actually, I asked my thesis advisor for my thesis if I could do this, and he says, no, it can't be done. He was at least right that I couldn't have done it. But also Unix came in the time frame where I would have been working, so it had been very embarrassing. But basically, C being a high-level language for what it was doing, it still didn't have function prototypes. I remember when I was told that function prototypes were dangerous. They were complicated, made it hard to read code, and would lead to bugs. After all, if you say square root of 2, it just shows you didn't know that 2.0 was what you should write, because you should know that it is floating point. And now the meaning of a call depends on the context, which you can't see, and this is dangerous and difficult. I mean, it was a different world then. Computers were expensive. $3,000 were almost real money in those days, and they had you couldn't really rely on a megabyte of memory, and certainly not of a megahertz. So this was a different world. And importantly for what I'm going to say here, everybody knew that object-oriented was slow, special purpose, and too difficult for ordinary mortals. I mean, simply, there was a few people who believed it could be done, but if you went to the average programmer or academic, the answer was, what? And out of the ones that knew about object-oriented, you were told this. I remember being told repeatedly by certified geniuses that if you want a virtual function, you just haven't done your analysis right. You mean you want to call a function and you don't know which one it is? You must be nuts. So the world has changed. This is not a proof that C++ is past it. It is just that every language we have is a response to a set of problems at its time. And then you go on forever if you are successful. Basically, the roots of C++ are very well known and was understood at the time. There are two lines of development that comes in here. We start from assembler through BCPL and to C, where basically we are trying to squeeze the last byte and the last cycle out of the system. We are trying to work close to the hardware, write things like device drivers, operating systems, and in those days also compilers and things like that. And the other line of development deals with abstraction. Fortran was the biggest improvement in the history of programming languages because it lifted the focus away from the hardware, from the machine, onto what's fit for humans. I mean, very odd humans here, engineers and scientists. But still, there was a shift in focus that's very important. And from it, you actually, accidentally, as it were, get portability. You can actually go from one machine to another. And once the engineers had theirs, everybody wanted one, and we got a total chaos of programming languages that couldn't interoperate. I mean, if I wanted to do some really nice computation on a database of some stuff or other, I couldn't do it, at least not in any reasonable way, because COBOL was how you dealt with records and big amounts of data on tape, and Fortran was the way you computed, and the two groups didn't like to talk to each other. Here comes object-oriented programming. That's Christian Nygaard, of course, who says, why do we build in these high-level abstractions into the languages? Why don't we instead give the programmer the ability to define their own abstractions, to define classes, class hierarchies, and such? And that came from there. And C++ comes from basically taking these two strains and putting them into each other. The reason was very concrete. I wanted to write something that requires a fair amount of complexity, which I needed to manage, and it needed to work directly at the hardware, so I had to be there. And it so happened that I knew these people. So it helped. I have a great depth to them. And from that, a lot of other things comes forward. In particular, C++ keeps moving. You see it fell off the screen here. Okay, so what is C++? In two lines, it maps directly to hardware in instructions and fundamental data types, and that came from C. That's the C inheritance. And the zero overhead abstraction, the notion that you need to abstract and you need to be able to afford to abstract. It initially came from Simula that had nice abstraction facilities, not perfect, that had weaknesses. I'll get to that. And it was certainly not zero overhead. I could not afford to use these techniques in the sort of the hardcore systems programming world that I had to live in. And much of the inspiration came from operating systems. I came out of microprogramming, operating system, hardware support for operating systems, that kind of world. That was my world and what I was thinking about. And so one thing I think about a lot is what does C++ want to be when it grows up? It wants to be that, but more and better. And that's its domain. There are other languages who want to do other things, obviously. One of the things the theme of what I'm doing is that with a language you're trying to do something, you're trying to enable something. Not everything. Different languages have different aims and different ground rules, so have to do this. By the way, I am very proud of have written a little book, 180 pages, that explains essentially everything about C++. This is 1,000 or 2,000 pages less than you usually get presented with. So here is the map to hardware, which is sort of one of the ground things I decided this is important for C++. Primitive operations become instructions. There are values, and there are other values that are sort of handles to values. Here we have pointers and such. And so you have int double, complex of double dates that makes basic values, and vectors, strings, thread matrices, etc. that are this pattern. This is borrowed with acknowledgement from C. This is where it came from. That direct map, I think, is a real beautiful part of C. Objects can be composed by simple concatenation. If you want a value kind of type that has two values in it, you put them next to each other, and what you get is two things put next to each other. A point made out of two integers, well, it's two integers. It's not two integers plus the time of day or any other helpful information that you might need in a different application domain. If you want the time of day, stick the time of day in there. You can do the same with the handles. So you can have a vector and a string, and you don't have the overhead. And everything maps down to memory, which is a sequence of fundamental units, usually bytes. And this was all in place in 72. But it's borrowed with acknowledgement. And basically, I had to make a few design decisions once I realized I needed a language because there wasn't one that could do it. Basically, I decided compatibility with C. I did not want to explain to people how to write a for loop. That was one of the way I was thinking about it. Why make a whole new bunch of mistakes when we already know and love Dennis's? And obviously C is good enough, and we can complain about them. If I did it, the likelihood is that I would make just as many mistakes, and they'll be new and therefore more difficult to deal with. Go with Simula, that's fine. I also needed generic types and operations. I mean, who really want a vector of doubles only? You want a vector of t, where t is an argument. And this here is in there in the first couple of weeks of the design. I wrote a paper and said that you could do it all with macros. Boy, was I wrong. However, I got the problem right. And if you get the problem right, eventually you'll get a solution. We'll see more about that. By the way, one thing that I didn't like from Simula is that they had this sharp distinction between user-defined types and built-in types. So a user-defined type, like if you make a complex or a point, has to be allocated on the free store, and in this case, garbage collected, and you have to access it through references or pointers or whatever you call it. When you have an integer, it can sit on the stack or be a member or be a global, and you can't have a reference to it. And I actually am really hard to see what's fundamentally different between a complex number and an integer. There are just two kinds of numbers that I use, and if I'm doing some kind of work that I want complexes, and if I do another kind of work I need integers, why should the language put in a sharp barrier in between? In my opinion, at the time, and still, there should not be such a barrier. And boy, have I been beaten up for making that decision, because that's what most languages in the next 20 years didn't do. The other thing that happens, probably in the second week, right about the time where I put in function prototypes, function declarations, I put in constructors and destructors. Constructor establish an invariant, acquire any resources needed to work, and the destructor reverses that operation. So from about the second week, C++ had a built-in mechanism for dealing with resources. We'll get back to that too. The other thing I decided, I was not going to hardwire concurrency into the language. My PhD was about concurrency mechanisms. I reckoned I knew about 25 to 40 ways of getting it wrong, and I wasn't going to hardwire any of them in there. Getting it wrong meaning good enough for 10 to 20% of your users. That's not a good thing. So this was in here very early. That's a much younger model of me. And by the way, one of the things that people talk about a lot in language design is how much better we can do it today. And I'm not sure I'm smarter than him. I'm actually pretty sure he was smarter than I am now. And in retrospect, I can say a lot of things, but you know, the designs has to work at the time in the hardware available with the programmers available, and he knew more about that than I do now. So I'm very reluctant to second guess that vintage, Bjarne. Later decisions, we got overloading. Interestingly, the first things was things like assignment to control transfer of values, and subscript, application operator, things like that. It was not plus and minus. As a matter of fact, and or came in first because somebody needed to write something to do with register simulation for hardware design. And one of the things I was quite keen on at the time was the idea that the language design had to be driven by real problems. No feature got into C++ after the first couple of weeks, unless somebody came to me and said, well, I have this problem. And usually my argument is, probably you don't. You don't need this. And then somebody else comes with a different problem and says, well, I have a problem. And if both of them can be solved by a single language solution, maybe I have something. I have abstracted from the particular problem into something that is more general. Put in exceptions, and notice that the mechanism for throwing an object and then catching by type, thereby getting grouping out of the class hierarchies, apparently was considered new and interesting at the time. It just seemed natural, but it has been useful ever since. Templates came in to get parameterized types. Importantly, both types and functions. I mean, why would I want a parameterized type if I couldn't also parameterize operations on it? And remember, I was never into this idea that every operation has to be a member of the class. I've never seen which class square root should be a member of. And I have never seen which class intersect should be a member of. So types and functions, types and value parameters. I really wanted to be able to parameterize something like a buffer. A buffer of what? A buffer is fixed sized, it is really zero overhead, it has to sit on the stack, or it has to be allocated in static storage or something like that. I really wanted my parameterization to be not just types, but also with value parameters. There I get into trouble with a type theorist. And I don't actually like to write types very much. So type deduction comes in very importantly. You deduce what you do. If I do an operation on a buffer, I don't actually have to tell for the call which kind of buffer I'm doing it to. The compiler already knows it, so why tell what the compiler already knows? So that came in there, and that came together with implicit instantiation. Again, a very touchy subject. If you look at something like Ada, for safety, security, efficiency, and such, you are required to say, I want a vector of integers, and now I want a vector of doubles, and you have to list them all in one place. I decided this was unmanageable and ugly, so I went for that. So trying to make it convenient, not trying to tell the compiler what it wanted. The other thing I did was multiple inheritance, which wasn't there before. It's especially useful for abstract classes, for interfaces. Before C++, the languages, by and large, were single inheritance, at least the more popular ones. And there were some research ones that were discussing things in terms of separating classes from types and such. But basically, this here, I decided was necessary, and that has been widely popular ever since. But usually not recognized for C++ because I didn't use the right terminology for it relative to what people decided 10 years later. Basically, one thing that I find very painful is this idea of what is the message you get across? How do you explain what you're doing? What do people understand? I tried very hard, and here is the traditional explanation. I started using it about 85 when I first had to give my first executive summary. You know what an executive summary is? It's something that fits on half a slide using very large print. And this was roughly, this is not it. It's too complicated for executives. But it's a general purpose programming language, has a by its source systems programming, it's a better C, supports data abstraction, supports object-oriented programming, and supports generic programming. Fine. And at the time, I then can go on, give an hour's lecture explaining exactly what this means, because this is not bullshit. This actually, I can back it with code examples, the language examples, the whole work. This is a good, solid description. This is useless as getting the message across. You end up playing blind men and the elephants with it, because people don't get that many words at once. They want something like this. C++ is an object-oriented language, which is what a lot of people went around saying it, and if Bjarne didn't understand that, he didn't get it. That was a very wide opinion at the time, and it still is. I just didn't get this. Well, no, I didn't get this. I didn't want to get this. Conventional, simple, popular, and wrong. But there's implications of this. If C++ is an object-oriented programming language, it's obviously not a very good object-oriented programming language, even if it supports object-oriented programming better than alternatives. Because you can do lots of other things that is considered noise. Like, obviously, C compatibility is a mistake if I'm trying to make an object-oriented programming language. There's nothing object-oriented about C. It's all about values and compact representation and parsing things efficiently. Also, furthermore, if you really think that C++ is for object-oriented programming if you think C++ is an object-oriented programming language, you must write object-oriented programming in it, right? So you must put all your classes in hierarchies. You must make your functions virtual. You shouldn't use C++ if you are not doing huge hierarchies of virtual functions. You have to get away with the freestanding functions, and generic programming is obviously evil. So this kind of thing led to a lot of misuse of C++ and a lot of uses of C++ that, in my opinion, was horribly complicated and very inefficient. Or people decide that since C++ wasn't the best language for this kind of thing, you shouldn't use C++. Now, this is sort of getting me into the myth of what people believe but just happens not to be true. And I wish I could control the message. I wish I could explain things better. But when you are dealing with languages, when you are teaching, when you are designing, try and make sure that you can get your message across so that people will actually try and use the thing in the way that actually works, as opposed to what somebody else does. Basically, people say they want a simple language. No, that is not what most people want most of the time. Teachers want to teach programming, all of programming, in 3 months. And researchers really want a simple language to manipulate and to invent extensions for. It's much better to have a simple language for that. And programmers want a simple language to start using so that they can feel sort of great after a short part of this semester or quarter. Developers, on the other hand, want comprehensive languages, and they grow over time. In my FAQ, I said, look, if Java survives, it will be much bigger, 2 or 3 times larger, and it'll be a much better language for it. This was what I said back in the 90s. I was right on all counts here. And everybody wants a single language, and they just want these 2 extra features to make it perfect. This I run into a lot. Yes, you should make C++ much simpler, and then I really want this and this. Okay. By the way, obviously, myth, not all myths are believed by all people, and not myths are untrue everywhere. These are sort of arm-waving summaries, but I hope I get the idea through. People want an intuitive notation. No, they are really, really in love with their previous notation, what they're used to. They confuse the symbol for the familiar for the symbol. And basically, this creates trouble. First of all, people want something like the C declarator syntax, which is seen as simple. No, it is familiar. Nobody, not even Dennis, would have decided a sort of a nested syntax, except that it was an experiment, didn't quite work out at the time, but everybody loves it. You can be an expert in it. This is good. And one thing that happens when you design syntax is people really want syntax because they are afraid of the new. So they want a loud syntax, prefix keywords all around. They really, really love it. Here, template, type name, container, void. Look, this was not the way I first designed it. But we would not have gotten templates into C++ and various languages, would not have been encouraged to add them later if I hadn't gotten past this syntax problem. People really wanted something like this. Just putting a parameter in here just didn't cut it. These days in C++ 14 we'll be able to say this instead to simplify it. Also, I really, why do you have a try in the front of something that catches exceptions? Why don't you just add a clause at the end that catches any exceptions? The compiler can't tell the difference. It's just a way for you to write wrong code and having a compiler message. But people really wanted that because they found that the fact that an exception could be thrown should be loudly expressed. Otherwise, people would forget it. They forget that next year they'll have learned all of this stuff. And they don't want to type the stuff, and they don't want to read the CRUD. And so it ends up looking like this. It's just a function call, and if somebody wants to catch something, they can do it somewhere. So we have this reduction. And here, in early languages, Simula and such, you have some kind of pointer or reference notation, and then you put it over on the FreeStore. A lot of stuff can be much simpler. As a matter of fact, this was, of course, what we had with C and all the older languages in the first place, but people wanted syntax. There's other reasons, but people really ask it. So basically, people scream they want an efficient language. I mean, teaching freshmen, first-year undergraduates, in the first month, inevitably, I found some smart aleck who was teaching all the other students not to use vector, not to use things like the sort, but be efficient. Use pointers and arrays and QSort. Good C stuff. It's efficient. No. They have mostly not even switched the debug feature off, and they're running 25 times slower than they would do. And so I got into the habit of waiting till I spotted it, till somebody stuck up their hand and says, you shouldn't use this because of efficiency, and then tear him apart. It's a good statutory example for the rest of the students. It had to be done, but people scream about efficiency. Go on the web, listen, efficiency, efficiency, efficiency. No. They will actually love things that, however slow, provided they it's convenient for them. And most researchers also really, when it comes to it, love inefficient languages. Then it's easy to write an academic paper about how to improve it. One of the great weaknesses of C++ was it's really hard to beat a virtual function call. After all, what is it? It's just an indirect function call, right? If you need an interaction, this is what hardware is good at. You can't write a fancier hash table to make it run faster or something. So they don't like efficiency either. Now, on the other hand, we do need efficiency. But by and large, you get popular by giving people what they want, not what they need. Anyway, I try to be in this domain. You don't need efficiency for everything, but you need it for some parts. And the parts where you need them are the ones I'm interested in. Let's see, language myth. We want a language for writing reliable code. No. Most programmers, most of the time, scream in horror when they have to do something extra for reliability, dependability, maintainability, all the good stuff. And most programmers don't actually care. They just ship when they're told to ship. I wish we were in a field with genuine professionalism, but I don't see much sign of it. This is not good. Okay, the brakes of this thing is programmed, and you better have the quality right. Okay, so is the steering wheel. There are places where this kind of stuff is absolutely essential, but it is not the way we have the discussion in the web, in academia, in education. They forget about it. This is somebody else's problem. Maybe it's a hardware problem. No, it's not a hardware problem. All the hardware is software controlled. Okay, so language myth. There is a best language for everybody, for every task, and one size fits all. People really love that notion. I mean, which language was dominant before C++? Which language is dominant after C++? In my opinion, there never was a dominant language. There was a dominant language called Fortran for computation. There was a dominant language for business applications called COBOL. There was a dominant language for this, that, and other. But there never was one language for everybody and everything. And I don't think we ever will have it. And this confounds things dramatically. Education, practice, research, language design, management, funding. All of this goes when people start believing that maybe we don't have the perfect language now, but we can get it. We'll just build it. We'll just throw some more money at this problem, or some more time, or some more advertising. It's just really bad. It comes back to the fact that we lack professionalism, but that's it. I hope you recognize the ring. So one thing that I come away from with this is we have to have a message. If you're doing something, in particular if you're designing a language, you have to have a message. It has to be simple, it has to be articulated, and it has to be repeated. And it has, of course, to be honest. I'm not talking about advertising here. What is the language for? What is it it's supposed to be good at? Who is the language for? What kind of people, what kind of programmers is it for? There is a difference between programming the central message bus of a BMW and programming your VCR. And sometimes when you listen to popular descriptions, they don't seem to see it. What would make the language better? Define better and be specific. I mean, I tried to say that for C++. I very rarely see papers on languages that are serious about articulating this, and especially saying what it's not good at. So basically, mapping to hardware, zero abstract abstraction. It's primarily industrial, and it rewards good programmers. In other words, it is not trying to be the simplest tool for everybody, for everything. Let's see. Oh, something else, but I forgot it. Now, if you manage to succeed on a large scale, you will end up with questions of standardization. I was told you can't have a major programming language controlled by a single company. I was told that by representatives of HP, Sun, and IBM that turned up in my office and says, you would like to standardize C++. I said, I don't think you want to standardize C++. It's not quite. You want to standardize C++. Okay, I'll standardize C++. So basically, this is not true. Java, C# proves that you can dodge standardization if you've got enough money and a large enough organization. And there's lots of kind of standardization. ECMA is the way you can basically buy your own. Sorry. ISO is the gold standard for standardization, and it's a real pest. But I thought it was necessary, and I've been living with it for a long time. And for good and bad, that's unusual for language designers. I think it has been worth it. But boy, it's painful. Long-term stability is a feature. And that's one of the things you get from a standards committee. If you have an owner, you get good advertising, you get resources to build things, but one of the days there will be a change in policy about what the language should be good for, and then you have to update all your code from all of your users and things like that. That's painful. Vendor neutrality is really important. It's important for some major users. Take people who ship on Windows, Mac, and Linux. It's not easy. Vendor neutrality is not something that's a feature, and deprived C++ for development fund for the fact that we were vendor neutral. There was no sugar daddy coming in with the money. And what is it? It's done by about 100 people at a meeting. I will be at one in 3 weeks in Switzerland, where we should do the final rubber stamp on C++ 14. There's 200 to 300 more online. I don't know what your view of a standards committee is. A lot of people have this vision of 3 or a dozen people sitting in a smoke-filled room conspiring against programmers. That's not the way it was. It's primarily industrial. They're primarily meaning that out of those 100 people that turn up, there may be 3 academics. This group is larger, has more academic, but it's still very massively industrial, and that's good, and it also hinders C++ in academic and teaching context. It's a very democratic process, one company, one vote, and there's people representing self, not your programming language, but the person. They can sign up for themselves. And there's no technical qualification for membership. Sometimes I wish I could set them a test in some basic programming, but you can't. People come because they want to and because they can afford the $1,280, And some of them are really good. Some of them has expertise beyond what we would have thought relevant, and it turns out to be relevant. This is important. The aim is consensus. We really, really do not like to get a feature in with a 60-40 vote. Those things don't stick. People go and do both ways. We really get somewhat unhappy unless it's a 90-10 at least. And really, if in among those 10s are some of the big players, we start worrying a lot. So it's a consensus building. It takes time. It also adds complexity. If you have a group of people together, you can't get something simple through. They want to do this and that and this and that also. So every feature, however innocent looking, can be a cancerous growth when it goes through the process for a couple of years. And that's a problem. Delays, of course. A committee does not have a coherent technical view. It's more or less defined. I mean, could you imagine us all agreeing on something major in detail? No, it just doesn't happen. So there is a problem of it's herding cats. And by the way, there's no formal organization to herd those cats. So tough. On the other hand, we get stability. Breaking old code is very, very hard and essentially never done. If the code was standard conforming, it makes it hard to set and maintain direction, and you can look up and get all the information WD21. A special issue about C++ is that we decided to have C compatibility, and so here is the family tree, and notice all of these things going around. And the versions of languages, I can find features in all of these examples on the Venn diagram. So C compatibility has been over the years a massive advantage both to C and C++ and a massive problem. It is really hard to maintain. The alternative seems to be to just go for the nicest language you can design and make a new one every 3 to 5 years. And it's not a way to build up a stable user community, but it's certainly a way of making progress on language design issues. Compatibility is a feature, valuable, expensive, and extremely hard. In particular, it makes it hard to correct mistakes. We had a couple of mistakes over the years, export, exception specifications, and the first version of concepts. We've managed to get them more or less out of the way, but not more than more or less. Basically, how do we define a language? And I have dealt with C and C++ for 30 years or more, and I can recommend to stay away from English or any other natural language. People love it, people think they can read it, but the precision is not right, getting the terminology right. Just figuring out whether something is compatible in C and C++ is hard because they use different terminology for it. In particular, we just recently found an incompatibility in the memory model relating to atomics because some genius over on the C committee rephrased it using the C terminology to say the same thing as the C++ design, but he got it slightly wrong. So English, no, that's not good. Compiler writers love it because by and large they like to write compilers, and there are relatively few type theorists there. And don't define semantics and character sequences, at least go to the ASTs. That way you can fix the syntax if you need to later. Even Algol knew that, but it had been lost. Bottom-up lambda calculus is too difficult, in my opinion. You should start at some level where you define it and say underneath it is hardware or is things. This abstraction we don't decompose. Virtual machines are not particularly good for defining things that want to work directly on the hardware. Once you have abstracted away the real hardware, it is hard to get there again. You just think you get it right, and then somebody invents a GPU or something like that. Formally described key interfaces. I'm not against lambda calculus. I'm not against formal specifications. I'm just saying you can't build them from the bottom up. You have to start at some level where you say these are the primitives. If you're not in total agreement with me, you can talk to Gabby Desrez down there, who's much better at it than I am, and formally verify the implementation of these interfaces. There are places for this. Okay. Interlanguage interoperability, it's a real pain. It's a real pain to real users. In C++, we tried to do it from day one with C and Fortran linkage, but there's no decent linkage specified for higher level constructs, classes, and templates. And we didn't go into the dynamic linkage because there was an operating system issue. I think this is a place where things fall down. They always fall down because inter-language operability and interoperability on things defined for different platforms is really hard because you need agreement from two parts at least, possibly three. Language A, language B, platform. Same thing over on the next platform. It is really, really hard, and of all the things that stops languages from being used, this is it, because it's really hard to get a new language in unless you get that kind of agreement. Also, a lot of languages designed that this is a new great language, and it's going to take over, and these other languages, you can use the old stuff, but you can't call back from it. Very nasty attitude, because no language, in my opinion, will ever be dominant enough to make that true. And if it happened, I would be very sad because we would be short languages. It's a massive problem. Teaching, another massive problem. A lot of people want to teach C first. So they have to teach you all the bad ways. What to do if you didn't have a function prototype and you did square root of 2. What to do if you don't have types coming out of your memory allocator. How do you report errors, etc., etc. Teach all the stuff that is difficult. How do you really do pointers to pointers? I don't use pointers to pointers. You only use them when you lack an abstraction so that the compiler can't build it for you. But anyway, all of that has to be learned, and that takes away most of these 3 months that we want to teach people how to program. That's very bad. And pure object-oriented programming, I've been there before. And I have an indicator, if you find a lot of macros or even attempted to write C-style macros, I'm not talking Lisp macros, C-style macros, you have a problem. It's either your design or the language. But certainly there's a weakness there. That's sort of one view of education. C++ did never manage to make a real community with a real center. This was because there was a lot of little feuding empires, Borland, Microsoft, IBM, GNU, and such. And they didn't talk to each other very well, and they did not agree on interoperability and such. We're still trying to solve that problem. The problem is that, that is a really, really major failing. The ISO Standards Committee can decide on language. They cannot decide on platform issues. And none of these little empires are not that little. N times 100,000 users is very common. I mean, just look at the Qt community. Hundreds of thousands of programmers, it is not the standard except at the language level. And again, this is hard. Okay, and large corporations really prefer languages they can own and control. And so there's always a weakness for a standardized language. Okay, I am running out of time. Should I say this? No, nothing more. Let's go to some code. I always feel bad if I give a talk without code, and so far it hasn't been enough. So one of the themes has been generic programming. It was there in the very first days, in the very first paper, and it was wrong with macros. Then in 87, I introduced templates into C++, and I knew what I wanted. I wanted something extremely general and flexible. I've always had the philosophy that if a language can only do what I can imagine, it's not good enough. I know my imagination is a small subset of the imagination of people in the room, and they don't all have to be language designers. Generality is extremely important. And this is actually not such a common design criteria, and certainly wasn't at the time. People are very often more concerned to make sure that stupid programmers can't do something bad. And now we can start discussing what means stupid and what means bad. Anyway, so very great generality, and zero overhead. I really wanted my vectors and matrices to compete with C arrays, which are basically the hardware. And of course we want well-specified interfaces so that we can get overloading, decent error messages, separate compilation possibly. Yes, I knew I wanted this. I was the one who put in function prototypes in C and C++. This is known. And if you've used C++, you will know I didn't get it. 2 out of 3 ain't bad, but it's not good. I don't think I had any choice. Nobody at the time knew how to do all the 3. I needed generality because I didn't want to limit what people could express. I needed efficiency because I didn't want people not to be able to afford it. And I didn't know how to do this. I mean, just put in a jump table, right? Make it an abstract class and put a type system around it. It's not that hard to do. I knew that at the time too, but it wasn't what I wanted. It didn't give me the vector and the generality. And it was probably the biggest success in C++ 98. I mean, the overuse of generic programming, templates, template metaprogramming shows how much people are willing to suffer to get what is being delivered there. It's really quite painful. Anyway, it's kept me working. And we can now do it. It's available in shipping. Basically, you started out with gave people containers, gave people the ability to use containers, and the old system was basically compile time doc typing. If it looks like an iterator and it behaves like an iterator, it's an iterator, and that's the way the system works. It's roughly equivalent to Python, except it's done at compile time, and the error messages come at compile time, and they can be spectacularly ugly. Anyway, so it's not good enough. But anyway, algorithms, and we can parameterize with containers, with elements, criteria, types, parameters, and do all of these kind of things. We can write code like this. Find if in the sequence from the beginning to the end the element is less than Griffin. That's C++ 11 lambdas. And the generic programming as practiced in C++ was originated with Alex Stefanov. And that's where we're going. That was a major success. But doc typing wasn't good enough. We really need better interfaces. And basically, we came after a couple of false starts to the notion a concept is a predicate on a set of types and values. For example, I want to have a type called that is sortable. A sortable is just a predicate. What does it take to be sortable? Well, you have to have a sequence. That sequence has to be random accessible, and the element has to be comparable with less than. Those are the 3 lines in the definition of sortable. And they're short lines. So you can define those. That's in something called a technical specification that comes out together with C++ 14 next month, I hope. You can download the implementation today. And so we can write these kind of things. So I'm very happy. This problem has been standing for 20 years. One of the things you must learn if you're in language design, patience and persistence. If you want to make something really major, it takes time, decades sometimes. And just because you can't do it doesn't mean that you can't do it in 10 years when you learn more. Okay, so here we have a sort that's sortable. I have a vector. I have a list initialized such. And I sort the vector. Everything is fine because a vector provides a sequence that is sortable. Fine. List doesn't. In the C++ standard, it says that lists do not have random access. There's no subscript operator. There's no plus to get n elements over. And the actual error message that come out, list of int, does not satisfy the constraint sortable. And if you flip the verbose switch, it'll give you 4 lines more that says that list of int does not satisfy the constraint sortable because list of int does not have a subscript operator. End of story. And we can get all the other good stuff with it, and the compiler is fast and simple, all of this kind of good stuff. And this leads me to something that is probably less revolutionary here than it is in most groups. I mean, generic programming is just programming, right? This is what we learned on about day 1 or 2 of learning to program. We have a square root, takes a double, uses double. Give the square root something that can be treated as a double, and you get a double back. Give it something that cannot be treated as a double, and you get an error right there. There's an interface defined here, and when you violate the interface, you get a good error message. You can do exactly the same with sort. Sort wants something sortable. Here's a vector. A vector is sortable. Everything is fine. A pointer to a vector is not sortable because it's a pointer. And so the problem goes away. So I think a lot of the myth in the C++ world about template metaprogramming and generic programming being a different skill is just shouldn't do it. The other thing that I've been dealing with, I'm actually ahead of schedule now. Thank you. Is resources and ownership issues. I mean, it came in the first week with constructors and destructors, but this has grown over the years and it's more important. But basically, I'll make a conjecture here. Garbage collection is neither necessary nor sufficient. It may still be good, but it is neither necessary nor sufficient for the kind of programming I'm trying to deal with. That requires proof. But I'll show you how we've done it in many cases to example. Basically, we need to build more systems to prove it. But garbage collection is not sufficient because a lot of resources are not just memory. A garbage collector collects memory. It's a memory collector. And things like thread handles, file handles, locks, sockets, containers holding non-memory resources like a record with a lock in or something is not just memory. And if you leak those, you have leaked something that is a system resource. So people invent finalizers to deal with this, and it takes them a few years, and they realize finalizers are evil, quoting the designer of Hotspot. And basically, it's not sufficient because they can't handle non-memory resources. The resource retention time is not good. The idea is that you hand over your cleanup to some system that cleans it up when it feels like it. In resource-constrained systems, you really want to free resources as quickly as you can because otherwise you need more memory, you need more file handle slots in the operating system, you need more locks, all of these kind of things. So you need to have resource retention time low. Distributed systems don't work too well. There's very few garbage collectors that can garbage collect objects you have left in Australia from a main process up here. So you start inventing patches for it, like leases and such. And NUMA memory makes it different in there. Also, let's see, did I? I think I forgot one really important thing here. A garbage collector is a centralized resource, fundamentally. You can start making it better by distributing the resources, the way they used in the old days for airplanes, of selling one block of seats to Amex and another block of seats to another company. And now you have to connect, and if you have to over-provision a little bit or you have problems. So in this very distributed modern world, having a fundamental shared resource is not a good idea. Even when you can mitigate this by trying to distribute the centralized resource, you're still trying to solve a problem you just introduced when you introduced the general resource. Okay, so what we're actually doing here in C++ is a resource is something that must be acquired and later released. That's a very general definition. I couldn't have expressed it as simply in 79, but I came very close. What I said was the constructor establishes the environment for the member functions to operate in. The destructor reverses that action. Very close. Anyway, so resource management should not be manual. We know people leak if they have to write things. And so we should automate resource management as much as possible. We don't want complex resource management, especially not in the hands of people, pointer manipulation, catch clauses all over the place to try and remember what needs to be destroyed. The dispose idiom is a partial solution, but it's still manual. I would like it to be automated. So the way I'm going about it is a resource should have an owner, usually a handle, and the handle should provide some well-defined and useful abstraction. So if I absolutely have to, I'll do a smart pointer, a unique pointer, a shared pointer, or something like that. But a pointer doesn't have semantics as such. The pointer has semantics, but you're really not interested in the pointer. You're interested in what it's pointed to, and the semantics gets messier. I much more like a matrix and a vector and a thread or something like that. Okay, so basically resources in the standard library, we have a whole bunch of memory-related resources and a whole lot of non-memory related resources, and they're all handled with a constructor-destructor pattern. And notice these can be combined. You can have a vector of lists of threads or something like that. So the mix of memory and non-memory resources happens absolutely natural in the way you write code and the way you think. And so we deal with it by control, life cycle, creation of object, destruction of object, copying of object. This is sort of where we were in 85 or thereabouts. And we can handle movement of objects now, and I'll show you how this is done. Basically, I'll do that next. And control access to representation, and at no cost. The zero overhead has been obeyed in this. And so the way it looks basically from the beginning is you have a constructor, you have destructors, you have some representation that's private, and I can do things like a vector of doubles, 1 golden ratio, pi, speed of light in vacuum, vector of strings, some language designers here, and at this point here, everything is cleaned up. This is why some people say that their favorite C++ language construct is the closed curly, because that's where all the interesting things happen implicitly without them having to think about them. You think about it at the design point. Now, there is one problem we had for years. How do you do a matrix addition? You take two matrices, you can pass them by reference, that's easy. And the obvious way of doing it is to make yourself a new matrix, fill it up with new stuff, and return it. But returning something from a function is defined as a copy, and this could be expensive. A 10,000 by 10,000 matrix is 100 million doubles, and even modern hardware can have problems with that. So it has to be optimized somehow. And the thing I observed is that even little kids, 6 months, year old or thereabouts, can handle this perfectly with no problem. Look, here's an object, right? It's now over here. I moved it. I mean, only a computer scientist would make a copy of this one, move the copy over here and destroy the original. This is just not... Look, so you knew that when you were 6 months old. So that's what we're going to do. Here is R as we're making it in here with lots of elements. We're filling it with good stuff. And the way we move them out is we take that pointer, put it in R, put it in res, and zero out the original one. Problem solved. And that's the move semantics that's now built into C++ 11, and we're using it. It sort of closes the loop for resource management. And that's why it's important. Here's some code just to show that things look different in C++ 14 than before. I find all V's in C, and I return a pointer to elements in there. And the way I write it, okay, make myself a container for all of these pointers, go through with a for loop, and see if it's the same. If so, I put it in there, and I return. And this, of course, vector has a move constructor, so this is an efficient operation. This is a performance bug in C++ 98. In C++ 11, it's efficient, so I can take something that's a container, like a string, and I can find all A's and M. I return that back. I loop over it and see if I really got A's back. It's just a test program. So the only purpose of this is showing that progress is actually possible. This is not a C++ 85 program or 98. I think I'm seeing some syntactic convergence. Here's a Python program, which is widely regarded as being readable and all of that. And here's a C++ 14 program. The main difference is, of course, that I like curlies. I'm not sure I like semicolons, but I have to write them. And here is the interface. It's a sequence. It'll take anything that is a sequence. So it'll take strings. It'll take vectors. Things like that. So it is not doc typing anymore. This actually has an interface check. Now, when I've shown this, people sometimes miss the point and says, this will not pass code review because people write too much code. Anyway, I wanted to show the code, so I'm going to do it line for line match. Of course, what you should do is the standard libraries, and this is a whole different talk, what makes a nice standard library. But here is the Python version, here's the C++ version. Here's another little feature. The empty list is the nil in anything that has kind of sequence semantics. Okay, I'm not going to go into the challenges. We'll talk about them the next 2 days, and I'll just take questions now.
Thanks. Let's do a question or two from the audience if you have them, and John, if you can repeat them for the recording.
I'll try.
Thanks.
So one thing I noticed you didn't actually talk about is tools in the evolution of language design. What are your thoughts on that?
So what is my talks about tools? Well, the reason I didn't talk about tools is that I had too much to talk about. The earlier draft actually had a cover slide saying tool chains. And in particular, I was going to talk a little bit about compiler technology and even more about static analysis, which I'm very interested in, and testing, which I should be more interested in, but I don't have any original ideas or experiences. And I just thought that for this particular talk, the most relevant part of the experience was to do with the language design, not the tools applied. I mentioned it in terms of interlanguage interoperability, which is a huge, huge tool problem, and the problem with different platforms is a big problem. But it's another talk that's longer than this one.
Yeah, you said something that was really interesting about, it's good to decentralize things and not have something centralized. But if you, this kind of touches on what comes first, the hardware or the standardization of the language. But if you look at the memory model, the whole idea of locks and sharing and whatnot, right? And that's what it's some way to shared memory in some kind of a multi-core or many-core chip. Wouldn't your argument of decentralizing things and implicitly message passing at the hardware level, and then wouldn't that kind of go against a little bit with the whole memory model approach?
So I'm not quite sure what the question is, but it has something to do with memory model and whether a memory model is forcing unnecessary sharing. I actually think that I'm trying to write the language in terms of what you can do on, say, a single core, a single thread of execution. And if you want to interact between multiple of those, you have to have something that's doing it. And how that's implemented in terms of atomics or locking mechanisms is a separate issue. The way C++11 memory model is defined, it is defined about what is valid, a valid single thread, and what then must happen if you interoperate with different threads. And all bets are off unless you follow the memory model. So basically, the fundamental thing is that there can be multiple independent threads of computation. So that is inherently distributed. And if you want to communicate, then you have to do something. It reminds me of what I was told by my advisor, David Wheeler, who was the assembly guy on my chart. Says, isolation is not hard, it's communication. It's granting access that's hard. And I think the right solution is to do fairly traditional things and then define mechanisms for sharing and communicating. Personally, I'm a great fan of message passing, but that's a different issue.
When I hope for in the language is something where I can get into that flow state where I'm effortlessly expressing my thoughts quickly in the language and trying them out with the computer. And with older versions of C++, as features were added and the book got larger, it got harder for me to get to that point in learning that language. And you talked about these languages have to grow. Is the book going to get smaller in the future? Do you have hope for that? Has it gotten smaller? I love the fact that you thought hard about making the error messages better, because that was a problem for me when I used templates before.
Okay, so the question is, we need to reach the level where we effortlessly express our ideas in the language, and that is the fundamental aim, to help people express their ideas. Languages don't solve problems, they help people express solutions to problems. And then languages under compatibility constraint tends to grow, and so we can get away from that. I had, as one of my main aims for C++11, making simple things simple. And there has been a lot of work that seems to be working there. The oldest feature, new feature in C++11 is auto. You can write auto x equals expression, and x is of the type of that expression. I first implemented that in the winter of 83, 84, and it was forced out for C compatibility reasons and because people couldn't think why they would want something like that. Another thing is you saw initializer list for abstract. You can define initializer list for your own containers and such. That simplifies how you express things. You don't have to do workaround. You saw the new for loops that are similar to in many other languages. They combine with, say, initializer list, so for x in this initializer. And so the report, and you have type-safe threading now, the concepts for constraining template things. All of these things make it easier and terser to express ideas. Now, unfortunately, there's all of this old code, and if you have to understand absolutely everything, tough. But there is a subset of the language that's easier to express and easier to teach and easier to use. And the first thing people do is not to maintain old code. The problem is with bad teachers, the first thing they do is to go through the evolution of the language, starting with the bad bits of C.
So can I get that book that's just that subset, and will it be smaller than
Close enough. It's called Tour of C++. It's written by me. It's 180 pages telling you what you wanted there, plus an index and a little history section.
Great.
So it's 190 pages. Yes, I've done it.
Thank you.
Great, thank you very much. I'm going to cut it off here for now. Since this was great, we do have a few more things on the schedule today. So we're going to take a short break now, like 5 minutes. I think there's still breakfast out there if you want to refill. And I would like you to thank Jana one more time.
Thanks.